Today we're looking at laws of logarithms. By the end of this, you should be able to express a single logarithm as two different logarithms, express multiple logarithms as a single logarithm, and solve logarithmic equations by applying the three laws of logarithms. So, I suppose we should start with the three laws of logarithms. The first says, if I've got a log and I'm multiplying two numbers together, I can split those two numbers apart by adding the logs of those two numbers together. For example, if I have the log base 2 of 5x, I can rewrite it as the log base 2 of 5 plus the log base 2 of x. If I've got two numbers being divided, I can separate them by subtracting. So the log base 10 of 4 over 3 is the log base 10 of 4 minus the log base 10 of 3. And finally, if I have some number to a power, I can take that exponent and multiply the entire log of the number by that exponent instead. So instead of doing log base 5 of 8 to the third, I can do 3 times the log base 5 of 8, which makes life a little bit easier. All of these come out of the exponential rules. For example, if I had two numbers, say I was multiplying 2 to the 2 and 2 to the 3, you add the exponents together. Well, that's what we're doing here. Instead of multiplying, we're adding. If we had something like 3 to the 5th over 3 to the 9th, you'd subtract the exponents. Well, that's what we're doing here. So, I mean, these come from the exponent rules. They're not anything new. They're just a new way to look at what we're talking about. Now, we're going to use these to rewrite things into different ways. So here we're going to express the log base 6 of m to the second n to the third in terms of log base 6 of m and log base 6 of n. So what I'm going to do first is, since I'm multiplying these two together, I'm going to use that first law and separate it into two equal parts. So instead of saying the log base 6 of m squared n to the third, I'm going to rewrite it as the log base 6 of m squared plus the log base 6 of n to the third. And now I'm going to use that third rule, saying that I can take any exponents and move it out to the front of the logarithm. So instead of saying log base 6 of m squared plus log base 6 of n to the third, I can go 2 times log base 6 of m and 3 times the log base 6 of n. And that would be how I could rewrite it. So I've got 2 times this logarithm plus 3 times this logarithm. Another way we can get this to look is, another way we can get this to do what we want is if we had fractions, and we could rewrite something with fractions in it. For example, this, log base 2 of the square root of m over n to the 5th. So what I'm going to do first is treat that square root as an exponent. So log base 2 of the square root of m over n to the 5th, well, since it's to the 1/2, log base 2 of m to the 1/2 over n to the 5/2. This will make life easier as we start separating things out. Now, since we have a fraction, I can subtract log base 2 of m to the 1/2 and subtract it from log base 2 of n to the 5/2. So that gives us log base 2 of m to the 1/2 minus log base 2 of n to the 5/2. And again, we'll use that third law that says that I can turn this into 1/2 log base 2 of m and subtract that 5/2 log base 2 of n. And that becomes how I can rewrite that. Now, you're probably saying, well, hang on a second, how can this be useful? Well, we can take things that look like this and work them backwards, so we can turn it into a single logarithm, and that could make our life better. So let's try that. We're going to express this as a single logarithm. So the first thing I'm going to do is use that third law backwards. I'm going to take this 2, make it the exponent of r. I'm going to take this 7, make it the exponent of p. So we get log base 10 of r squared plus the log base 10 of a minus the log base 10 of p to the 7th. Now here, in this set of parentheses, I'm adding, so I can multiply these two together. Log base 10 of r squared times a minus the log base 10 of p to the 7th. I was using the first law of logarithms. Now, since we've got a minus sign, we're going to take r squared a, make it the numerator, and make p to the 7th the denominator. Log base 10 of r squared a over p to the 7th. And that is our single logarithm. And again, I'm hearing you say, well, why on earth would we want to ever do that? I don't see how that's useful. Sometimes your teacher will be nice enough to give you values for logarithms. And if that's the case, then we can start rewriting logarithms so that we can solve them without the need of a calculator. Well, without much of a need of a calculator, especially if your calculator doesn't do logarithms. But sometimes multiplying decimals can get a little ugly. So for example, here, I'm telling you, log base 10 of 2 is 0.3. Log base 10 of 3 is 0.48. And we're going to rewrite these two logarithms so that we can find values for them. Here we've got log base 10 of 18. Well, I'm going to rewrite 18. 18 is 2 times 9. So 18 is 2 times 3 times 3. So log base 10 of 2 times, let's make it 3 squared. 3 times 3 is 3 squared. Let's use the laws of logarithms. Since I'm multiplying, it's log base 10 of 2 plus the log base 10 of 3 squared. And since I have this exponent, I'm going to move it out front again. Log base 10 of 2 plus 2 times the log base 10 of 3. Now, I give you the log base 10 of 2, which is 0.3. So that's 0.30 plus 2 times 0.48. You multiply this out, add the 0.3, you end up with an answer of 1.26. So there's your answer. So if I raise 10 to the 1.26 power, I'll get close to 18. The reason I say I get close is because these are approximate values, so it may not be perfect, but it's close enough. Now, if I have something like log base 10 of 1 to the 1 over the square root of 2, the cube root of 2, looks a little trickier. Really isn't. You've got the log base 10 of 2 to the negative 1/3. So that's negative 1/3 times the log base 10 of 2. Log base 10 of 2 again is 0.30. That times negative 1/3 gives us an answer of negative 0.10. And there's your answer. 10 to this exponent of negative 0.1 gives us around about 1 over the cube root of 2. Now this is all well and good. We can get values now. So what we can do now is solve some equations. So here we have the log base 3 of x plus the log base 3 of x minus 6 equals 3. Since we have two logarithms being added together, I'm going to use that first law of logarithms again and multiply x and x minus 6 into one single logarithm. Log base 3 of x squared minus 6x equals 3. Now I'm going to rewrite this in exponential form because I can solve equations that have exponents in them, but I can't really, with the logarithm there's not much we can do right now. So I'm going to rewrite it in exponential form. The base 3 to that third power is x squared minus 6x. 3 to the third is 27. If I subtract 27 from both sides, I get 0 equals x squared minus 6x minus 27. So let's factor this. If I factor this, I need factors of negative 27 that add up to negative 6. In this case, negative 9 and positive 3. If I add them together, I get -6. If I multiply them, I get -27. Fantastic. So, our factors are x minus 9 and x plus 3. Which means our two solutions are x equals 9 and x equals -3. Now let's think about this for a minute. There's no number that I can raise 3 to make a negative number. Everything remains positive. So that means that this here is incorrect. That doesn't work. -3 doesn't work. But let's check 9 to make sure that it does work. We have to check our answers because otherwise things may go haywire. So if we check our answers, then the log base 3 of 9, this is our check, log base 3 of 9 plus log base 3 of 9 minus 6 needs to equal 3. Now the log base 3 of 9, 3 to what power gives me 9? Well, that's 2. 3 squared equals 9. 9 minus 6 is 3. 3 to what power equals 3? Well, that's one of our identities. It's 1. So does 2 plus 1 equal 3? Yes, it does. So our answer is 9. That's the only answer we have. So the laws of logarithms really come in handy when we want to rewrite something or we're given values for logarithms and we could figure out its actual value for the whole thing.